Snowy Forest Productions presents.
Siege Productions presents a custom 7-segment display driver.
Hi. Focus. Hello. And welcome to this video. So, there was an old chip called the 9368. And this old chip was able to take 4-bit binary data and directly hook up to a 7-segment display and display the data in hexadecimal. It would sure be nice if the classic 7447 7-segment display driver would do that, but it doesn't. It is only made for BCD or binary coded decimal, or the digits 0 to 9 to put it into layman's terms. So I don't have any spare 9368s, but I discovered this chip in the old 1980s manual 1 byte at a time EPROM programmer, which I have made a video of earlier. And I want to make what's almost an equivalent. That is just a device that will do 4-bit binary to hex on a 7-segment display. Now, I can't get the full functionality the 9368 could do. For instance, the 9368 would automatically current limit the outputs, so you could directly hook up a display without having any dropping resistors. We'll still have to use dropping resistors on this, but at least I'll be able to do hexadecimal, 4-bit binary to hexadecimal with the chip. The idea will be to use the N82S123 32-byte programmable read-only memory, and it's a vintage chip, and I have a bunch of these old vintage chips unprogrammed, and I'm not going to program all of them like this, but I might do 1 or 2. I don't know if they'll end up being used in a project or not, but it'll be neat to at least show it in operation. Of course, the starting out phase, I put the code for it on an EPROM. So if I made a mistake, which I did at first, I wouldn't have to use up a precious chip. Enjoy.
Okay. So we look on this paper.
This is a 7-segment display. Notice the segments A, B, C, D, E, F, and then the middle segment G. Different 7-segment displays can have different pinouts, but a common pinout is here. I put true because I had drew one earlier that I made a couple mistakes on, so this is the corrected version. And DP is decimal point and CA is common-anode. And then I used it's literally 2017, and it's just time just goes by so fast. But if you're wondering what pencil I used a Uni Kurutoga for this page here, high grade version. 2716 EPROM Pinout, beautiful chip. Make sure for reading it you tie this pin low for enable. This pin I believe is gate. Tie it low. Tie VPP high. I tried tying it low earlier and it wouldn't work, so tie it high to 5 volts and it will work, but obviously don't apply the higher programming voltage to it. So this is the pinout to the 2716 EPROM. Address pins are the A's and data pins are the Q's. Least significant bit is the one with the 0. Most significant bit is the highest. Then this is the 7493 4-bit binary counter pinout. When making this binary counter, tie pin 12 to pin 1. And these are both master resets. Tie them together, and then it's active high to reset, because they both internally connect to an AND gate. Or you can tie one high, and the other one by itself can be used as the reset pin. And then you have your outputs with Q0 being the least significant bit. The counting clock input you want to do is clock A. Then these, in my little deal here, are what pins. These are the crossed out errors ones. Most of them are right, just a couple of them are off. What output pins from the read-only memory are going to drive which pins of the 7-segment display, of course, with VCC going to pin 3, and of course remember your resistors. 330 to 470 ohms is a good resistor range. I used this little deal here. It looks like a dip packaged chip, but it's kind of a yellowish color and is just a set of 8 330 ohm resistors. You could always use discrete resistors if you desire. It was just easier to use this part, and I happen to have a bunch of them on hand, so hey, why not?
This is just a rehash of what data pins go to, which this is whenever I was designing the code. Machine code, I guess you could sort of say. But it's not going to any microprocessor or anything. It's just converting one form of information into another. So the digit here also would directly correspond to the address coming in. You know, whatever your binary counter's at. And then after you go to hexadecimal 10 or 16, it just blanks out the display. I put the binary. Since it's a common anode display, that means to light up a digit, you want to feed a 0. So 0 in this case is on, and 1 is off. If you want to use a common cathode display, all of the binary / hexadecimal code here must be inverted. That felt good. So I did the binary, which was easily translated into hex, and I don't know how clearly you can see this whole thing, but just in case you can't, I'll go just in order. 0, 1, then 4F, then 1, 2, then 06, then I should see 06. 4C, then 2, 4, then 2, 0, then 0F, then 0, 0, then 0C, then 0, 8, then 6, 0, then 3, 1, then 4, 2, then 3, 0, then 3, 8, then all the rest is 7F. All the way to address 1F in the ROM. Here on this vintage, when I checked inside, copyright date on this breadboard is 1980. This vintage proto board 102A has a 5 volt fixed power supply. It also has two 15 volt power supplies, plus and minus 15 volt, which I'm probably going to convert to adjustable. But that's beside the point. Here is the circuit. This extra counter is not being used. This is just logic probe wires. So, anyway, you can see right now I have an EPROM on there. The old 2716 EPROM, 1982 vintage. And I got all the unused pins tied low, except, well, technically these are being used to enable the chip here. and VPP is tied high. Unused address pins are tied low. This is just a resistor array that's just tied to low, just to make it easier to connect instead of using a bunch of individual wires, because I had a bunch of those on hand too, so why not? This is a reset switch. Reset is tied low through a 1K resistor, but this switch connects from 5 volts to the reset pin, so if I push it, it resets, and there's no need to debounce this just to show it on operation, because I'm receiving pulses from a pulse generator and they're being monitored on this LED, and the pulses go into the pin 14, the clock input on this 7493 chip, which is sending 4-bit binary to the lowest nibble of the of the 2716 EPROM, and then the data pins Q0 through Q6 are driving the segments through this resistor array here to a common-anode 7-segment display. So let's turn it on and let's reset it. So it's a little bright, I guess. I'll just zoom in. I don't know how well you can see this on the screen. It says 0. So we have our pulse generator here. So let's set this. Okay. I can do single pulses, I can do continuous pulsing, and then I can do bursts of however many pulses I set on this. So let's first show single counting manually. See, I have no tripod because my tripod is 24 hours away in Arkansas. So I ain't getting that thing anytime soon. I know, it looks like it says 8, doesn't it? It says 0. Push it. Am I pushing the right button? I am. 1. Oh, I see. I'm watching the computer, which lags. 3, 4, 5, 6, 7, 8, 9. And then hexadecimal for 10, which is A. And then B, C, D, E, F. And then it goes back to 0 because it's only 4 bits. Make sure if you're making one of these, your 6 has the top on it, because you don't want it to be confused with the letter B. Now when it comes to the number 9, it really is your choice whether you have the bottom half on it or not. I decided not to put the bottom piece on it, and it just goes like that. That was just my personal preference with making the 9 on here. But you can do it either way. So, this little counter is pretty cool in itself. The HP8011A pulse generator. Yes, made by the same Hewlett-Packard who nowadays makes crappy printers. Well, they also were known for making a renowned high-quality electronic test equipment, such as this pulse generator and this pulse counter and other various different devices. So, this, I can set a number of pulses. Let's say I only want to do 3 pulses. I can do a single burst. Oh, goodness, you can't see anything. Okay, so I set this to 0 and I push single burst, and it will send out a series of 3 pulses because I have it set to send out 3 happy-go-lucky pulses. Of course, that was a little slow, so I can increase the frequency of it, and it looks like it's almost immediately showing a 3. It's pretty cool. Let's say I want to show hexadecimal A, but I want to get to the point. You know, I don't want to wait. I just go, and there you go. Or let's say we want to show hexadecimal for the number 15. We just go, and there's an F. Now let's say we want to illustrate that the powers of 2, 16, and above are all multiples of 16. It will show that by being 0 every time. I'm going to make it send out 64 pulses, and it's going to say 0 again. And you can see it still says 0. Well, it didn't. It counted through 64 times, then landed at 0, to be more precise. If we do 65 times, you'll notice it says 1. Look at that. Pretty nifty, huh? Do another 65, and it's as if it were counting up. Pretty nifty, huh? So that is the device to it's custom, a custom display driver. But I also want to use a very old chip that I got excited about, the 82S123. Programmable read-only memory. Oh yes, from the fantastic year of 1984. We're going to take this very special N82S123 32-byte programmable read-only memory and put it in our EPROM programmer. Here is the EPROM programmer, the Advantech Lab Tool 48 XP upgraded version from 1997. So we will take our little bitty PROM. It just looks funny being put in the programmer because it's made for bigger chips. Without depth perception, looking through the viewfinder, it isn't quite as easy to insert the chip. Our old pal the chip, a blank PROM, now resides in the EPROM programmer's zero insertion force socket. What a thing it is to behold. Using some of the most advanced screen capture software known to mankind, let's open up the EPROM programming tool. Okay, now we go. Oh gosh, I'm probably blocking the screen too, am I? Oh, maybe not. Okay, good. Load. Now we have this already. I wrote the program or the code. Wait, it's hex 7 segment dot bin or bin, depending on how you want to pronounce it. Binary file, buffer size 20 in hex or 32 bytes. Read completed. 32 in parentheses, 20 in hex, bytes read. Now we go to select and we choose our chip of choice, because obviously this is not a 2716, it is the 82S123 PROM, and there it is, select. We go to edit, we see the code that I wrote, which I had shown earlier on the notepad. We select OK. Oh, and this is where it gets good. Let me just check, make sure that thing that's been corrected from last time. I hope I'm not blocking the blooming screen.
Okay, good. 4F. That's what I want to see. So now, because these are only one-time programmable, okay? These aren't even the OTP EPROMs that are technically have an EPROM die inside, but no window. This is, it blows the microfuses. It literally, you're literally blowing little tiny fuses inside the chip when you program bits onto it. So, oh gosh, here it is. Everyone, brace yourselves. Let's make sure it's not blue. This is a moment that has to be captured, okay? Everyone brace yourselves. I'm about to program a PROM. A blank PROM. Device, oh, really? It's not blank? Read. Oh, come on. What's this nonsense?
It wasn't labeled, but it was programmed. Let's try another one.
It's not blank, is it? Edit. It's got the same trap on there.
Okay, that's not good. Those were two that were found inside that cardboard box full of old chips. These other ones, I imagine, are blank. Because these ones are already inside the organizer drawer, so they're probably blank, hopefully. I hope. They better be.
Watch it not be blank. Oh, yeah. Oh, yeah, blank check complete. That's what I want to see. Two of these 82S123s are not blank. They were from a different batch of chips. They weren't labeled, but they were programmed. So they're just pretty much useless. Okay, now, everyone brace yourselves. First things first, load it again because the buffer had been changed to something else. Okay, edit, we make sure our code is in there. Okay, it is. Make sure we don't have the blue screen of death Windows Movie Maker version. We don't. Okay, now we... watch. Oh, it's been programmed. Now we read, edit. There it is. This PROM has been programmed. Believe me, it's a programmed PROM. Oh, okay. Unbelievable.
We now remove the illustrious PROM from the programmer. Turn off the programmer.
Here it is. Here it is.
A programmed 82S123. I'm back again. I have built a circuit utilizing the PROM, and we'll show it in operation driving the 7-segment display, successfully converting 4-bit binary into hexadecimal. Here is the circuit. Now, first, before we get into the circuit... Okay, so here is the pinout for the illustrious 82S123 32 by 8 or 32 byte bipolar TTL PROM, programmable read-only memory. It's a tri-state output device. When chip enable is held low, the outputs are energized.
When it's high, they are tri-stated off the bus, if there's a data bus, which this doesn't really have much of a data bus at all. So you have your 5 address pins, A0 through A4, A0 being the least significant bit, A4 being the most significant bit, and I'm using it as the blank display input on the program that I wrote. Another thing to keep in mind is whenever I looked at the data sheet, I was like, all the outputs are labeled as O1, oh, these are actual O's, not zeros. O1, O2, O3, and I was like, I wasn't sure which one was considered least significant bit, which one was considered most significant bit, because I've seen it done both ways. But it turns out the least significant bit is output number 1. And I'm not even using output number 8 in this, so it's program 0 regardless of what the address is. So I have the 82S123 of 1984 vintage loaded up on the breadboard, hooked up through the resistor array, and to the 7-segment display with my 4-bit binary counter. So let's turn it on, reset, and we get 0. Okay, so this breadboard, no nice thing about this powered project board here is that you can actually set it vertically because of the casing. So I set it vertically on this table, and I'll be able to show this display nicely. I would put my exposure way down on my camera. Now I know the 0 is a bit blurry. I have the camera about focused as well as I can get it. But I've turned the exposure way down so you can definitely, without kind of just the over brightness look, see the 7-segment display very nicely on the screen. So now we'll demonstrate the counting. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then hexadecimal for 10, hexadecimal 11, hexadecimal 12, hexadecimal 13, hexadecimal 14, hexadecimal 15, and then back to 0. And of course we can send out sets of pulses, 5 at a time, for example. Reset the counter, and we can send out 7 pulses. Reset the counter. We can set out, how about 12? It's going to give us a C. Oopsies, wrong button. Wrong button again. Jeez. Embarrassing moments 101. There we go. It says I keep looking away. Keep looking at the monitor screen and all that, and I'm not. So I go to push the button and then I push the wrong one. It's like, that's 12 pulses each time. How about 14 every time? Pretty cool. Then I can just send out continuous pulses and just pretty cool. Yeah. Pretty cool. Okay, so anyway, I hope you enjoyed this video. Making a custom 7-segment display driver. Using the 82S123 32 byte programmable read-only memory chip, which in itself is expensive. You can get them on eBay, but they're expensive. I got lucky with mine and got a whole bunch for literally free, with tons of old electronic, components and some test equipment and stuff given to me recently by someone who didn't need it anymore, and it had just been taking up space in his house. He was glad to get rid of it. And anyway, so yeah, hope you enjoyed this video. Of course, you can always use other forms of programmable read-only memory, double EPROMs, even any kind of device, device to take a binary address and give you out some data, and you can make a 7-segment display drivers. These chips are just useful for various different things. Obviously, the actual use would be to store programs, but anyway, obviously the programs that would go in here would be incredibly small, considering you only can have 32 bytes worth, which is hardly anything. But anyway, it's a good illustration of use of this chip in a way that it was not quite intended to be used for, as a display driver instead of just a read-only memory. But really, if you think of it, a display driver is a form of read-only memory. Another idea I have, if I ever get a hold of some alphanumeric displays, is the idea of putting ASCII, direct ASCII, into the address lines of an EPROM, and getting the display driver to display the letter or number corresponding to the ASCII. And the idea would also be that if there was a lowercase ASCII code coming in, it would display the uppercase version of the letter, because not all the lowercase letters can be properly displayed using an alphanumeric display. I don't have any alphanumerics, but if I ever get some of those, I'll probably do an experiment like that, just for the sheer fun of it. Anyway, viewers, goodbye. Hope you enjoyed this video. Yep. Hope you enjoyed it. There's no point in saying like, subscribe, and all that nonsense. It's not even any reason to. I'm not even a partner on YouTube, believe it or not. I had the chance to become a partner at one point, on YouTube. But I decided not to become a partner because, well, A, the amount of money I'd make on the videos would be negligible, probably, because I don't get enough views. And B, even if I did become a partner, I don't know if this would be the case for sure or not, but I just am a little afraid that they might come a little bit more strict and crack down on the videos that I've uploaded in the past where I play copyrighted music, because I'm displaying the music recording quality of a tape recorder, and of course the music's going to be copyrighted because it's just music. And I was just afraid that if they cracked it down more on that, got more strict with it, I didn't want to risk possibly getting my YouTube channel deleted. I have over 800 videos on here. I don't want this channel to get deleted. That would not be good. That'd be a lot of data, history, and stuff just gone. Plus, maybe there's less ads you guys have to deal with. But either way, I will always recommend AdBlock Plus. It is one of the best programs created by humankind to date.
Arch nemesis, 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 arch nemesis.